You're going to make very long, very big errors. So I think it's hard to use a robust verification to talk about vision errors. Plus, if the bounds on your robustness are so large compared to your control authority, robust design isn't going to give useful solutions anyways. So we've increasingly been changing for that project, thinking about stochastic verification. And the Lyapunov story works actually surprisingly well for the stochastic case. Okay, so there's a direct analogy to the Lyapunov theory for stochastic system. If I can find a scalar function now, I have a stochastic dynamical system. If I find a scalar function which the expected value is going downhill all the time, it's called a super martingale. Okay, and you can still use a super martingale to bound the probability of leaving some region. The same way it used to be, I got set invariance. I used to say I'm never going to leave this region with probability 1. Now, if the expected value is going downhill all the time, I can use some Markov inequalities and get a bound on the probability of leaving some level set. Okay, and it turns out we can search for those with the same sort of optimization. It's a harder search because Lyapunov functions are very flexible. So Lyapunov functions, if I find one Lyapunov function that works for a system, I can multiply it by 2. I can multiply it by, I can do things to it, and there's still going to be a Lyapunov function to the system. In the stochastic verification, the steeper the function we verify, the tighter my bound. So I've got a lot more incentive to look over a smaller class, or a tighter class of functions. So we do it by now looking over exponential quadratics or exponential polynomials in general, which are sort of the fastest growing thing you can involve with a Gaussian. If you have a nonlinear system with Gaussian noise, it's sort of the fastest growing function you can involve with a Gaussian and still get an analytic form out.
Do you need an a priori bound of JP?
Just positive definiteness.
No upper bounds in the spectrum or anything like that?
Unless we missed something, I don't think there's any upper bound.
Well, I mean, morally, in time-varying system settings, we're trying to do something like a solve. Then sort of these invariance theorems, you need the derivative to be bounded above by something that is not time-dependent. And it's not just it can be negative. It's bounded above by something negative and time-independent.
Right.
If you want to leave the JT in there, so somehow conservatively you want to bound that by something time-independent, if you allow me to do that.
Right. Okay. So we don't consider sort of adversarial JTs, but I agree. So in our statement of the theorems, we're careful about all these things. But in practice, JT is, we search over, we try to minimize things on it, and it's a bounded search over positive J's. Yes. And in fact, most of the cases we've done are with static theories too.